Hi, welcome to this lesson on finance, future value annuities. Let's take a look at what a future value annuity actually is. So by definition, a future value annuity, as the name suggests, is a plan to save up for the future by making regular payments into an account that will accrue interest over time. So such examples of future value annuities include things like saving up to attend a tertiary institution after high school, or if you're working, you would save up for a retirement plan or pension fund, and so on. We can actually calculate how much money we should be saving each month or each year, whichever time period we're using, to achieve a certain amount for the future that we want. Generally, when we invest money into a bank account, it is done on a monthly basis. That is the norm. And this is usually compounded monthly at a certain interest rate that is defined by the bank. Let us analyze an example to see how we can derive the future value annuity formula. This is the formula that we're going to be using whenever we solve any type of future value annuity problems. So, let's have a look at this example. At the end of each year, that's really important, that's telling you when, at the end of each year, for 5 years, Kyle will deposit 600 Rand into an investment account for a new phone that he will purchase. The account offers an interest rate of 12% per annum compounded yearly. Determine the value of his investment at the end of the 5 years. Now, looking at this problem, we see quite a bit of information. We have our principal amount P of 600 Rand that Kyle's going to be depositing at the end of each year for 5 years. The interest rate is 12% per annum compounded yearly. So that is an effective interest rate because it matches up with the time period being years. And we can use the compound interest formula, that being the accumulated amount A is equal to the principal amount P times the quantity 1 plus the interest rate, all raised to the power n. So we have our yearly payments of 600 Rand and the interest rate of 0.12, which is 12%, being the effective interest rate, meaning that it matches up with the time period of payments. The amount of time is n equals 5 years. Let us analyze what happens after each year that Kyle deposits the 600 Rand by using a timeline. Right, so timelines are vital whenever we solve anything in financial mathematics, as it helps us to visualize very clearly when payments are being made into an account. Okay, so we construct the timeline as follows. I'm starting off at T0 and ending off at T1. That timeline there, that gap represents 1 full year. And notice I don't start at T0, I start at T1. Because of the context of the question, I'm putting the 600 Rand at the end of the year. Okay, then you see that's going to be 2 years here. By T2, that's the end of the second year. Then it's going to be 3 full years by the end of T3. Then it's going to be 4 full years by the time you end at T4. And it's going to be 5 full years by the time you end at T5. So look at that. Kyle's putting 600 Rand at the end of year 1, 600 Rand at the end of year 2, 600 Rand at the end of year 3, 600 Rand at the end of year 4, and at the end of year 5, he makes his last 600 Rand deposit. And we can analyze what's happening here. At the end of the first year, so 1 year has gone by. That means at the end of that 1 year, 600 Rand gets put into the account. So it leaves it how many years? 1, 2, 3, 4 years of interest to grow. Similarly, as that's growing, he inputs another 600 Rand here at the end of the second year, and that one will have 1, 2, 3 years to grow. Then at the end of the third year, he puts another 600 Rand, which will have 2 years to grow. At the end of the fourth year, he puts a 600 Rand, that'll have 1 year to grow. And at the end of the fifth year, he puts 600 Rand in, and that doesn't grow any interest because at that fifth year, he just simply puts 600 Rand in, and then whatever that total amount sums up to, that is how much Kyle will have at the end of 5 years. Okay, so as we said, the first deposit in the account will earn the most amount of interest, 4 interest payments, and the last deposit will earn the least interest, no interest payments. So we can summarize this information into a table as follows. So let's look at the years, the deposit that Kyle makes, the number of interest that payments will accrue, the calculation, and the accumulated amount. So like we said, at the end of year 1, he put 600 Rand, so that'll leave him those 4 years, as we saw here, 1, 2, 3, 4 years to grow. And we can use the formula A equals P times 1 plus I to the power N, where I is your interest rate, and it's an effective interest rate there, 0.12, all raised to the power 4, because it goes over 4 years. And you can do that in your calculator, you'll get 944 Rand and 11 cents. The same thing is true at the end of the second year. That has 3 years to accrue interest, and then you arrive at that amount. For the end of year 3, you have 2 interests. At the end of year 4, 1 interest. And at the end of year 5, we're simply just putting 600 Rand in, so there's no interest. And you can see that there, it's just 600 Rand. So all this money is growing over time, and you have a total amount of 3,811 Rand and 70 cents. So that's how much Carl will have saved up by putting 600 Rand as regular payments. And you can see this is worthwhile because, for example, we only had 1, 2, 3, 4, 5 amounts of 600. So 5 times 600 is 3,000. So you only really put in 3,000 Rand over the 5 years, but at the end of the 5th year, you actually get 3,811 Rand, 70 cents. So you gathered another 811 Rand and 70 cents just from interest alone. Okay, so that's why it's important to save up for the future in an account that accrues interest. All right, so now we will now derive the formula for the future value annuity as follows. So let us recall that for a geometric sequence of the form T sub n, a to the times r to the power n minus 1, where n is a natural number, the geometric sum or series formula for the first n terms is given by the following formulae. So you would have learned this in our geometric series topics. And essentially you have 2 different formulae, but they are equivalent just depending on your constant ratio value. Okay, so it's given by either a times r to the n minus 1 all over r minus 1, or a times 1 minus r to the n all over 1 minus r. So that is the sum of the first n terms in a geometric sequence. But why is that relevant here? Well, in the practice problem above, we can actually calculate the total value of Carl's investment at the end of the 5-year period by summing, so that's where we're getting our series from, the amounts for each deposit. So that 3,811 Rand and 70 cents that he got was essentially made up of the 600 Rand that was at the end of the 5th year. Then that's how much would have happened by the 4th year, the 3rd year, the 2nd year, and the 1st year. So these years just means, for example, at the end of the 1st year, when you put 600 Rand in and you let it grow over 4 years' time, you get 944 Rand 11 cents. But each of these values can actually be written as follows. So if we write it like this, in terms of the formula A equals P times 1 plus I to the N, then all of these have the same P value, that initial investment of 600 Rand, and it grows over 1 plus 0.12, and you can see the power here, 0, 1, 2, 3, and 4. So there's a constant ratio of 1 plus 0.12 that gets multiplied by the previous term to get to the next term. So this is actually a geometric sequence with a constant ratio. And notice this value here is going to be 1.12, which is greater than 1. So we are actually going to end up using this first formula here. All right, so we can use the formula for the sum of a geometric series with the following parameters. Your starting amount A is 600, your constant ratio is 1.12, and your n equals 5. So if I plug that into the sum formula, you see we get the correct amount without having to do that lengthy calculation. So if we just know the principal amount, the period of that we're going to be investing, and the interest rate once you've done 1 plus I, then you can use the geometric series formula to derive this solution. Okay, so now we're actually going to use this sum of a geometric series to derive a formula for the future value, which we will call f, of a series of n regular payments of an amount which we will call x, so essentially which are subject to an interest rate I. Okay, so essentially here the parameters of the geometric series are the starting term A is that x amount that you are investing, your interest rate or your constant ratio R is 1 plus the interest rate, and you have n payments. So if I use the formula here and simply substitute A for x, R for 1 plus I there, and I clean up the geometry, at the top here it is simplified as possible, but at the bottom we have 1 plus I minus 1. So the 1 and negative 1 cancel and you're left with I. Okay, so hence the formula for the future value annuities is given by the future value that you will have by saving up by making X regular installments. So this is your regular installments or regular payments, will be the regular installment times 1 plus the interest rate times to the power or raised to the power n minus 1 all over the interest rate. Okay, so this is the really important formula that we're going to be using. Okay, so when using the future value annuity formula, the variable of the time period n needs to be interpreted correctly. Let us look at an example where we need to use a timeline in order to get the correct number of payment periods. So example, Kyle makes his first payment of 500 Rand into a savings account on the 31st of January 2023. He continues to make monthly deposits of 500 Rand at the end of each month up until the 31st of March 2028. The interest rate was fixed at 6.5% per annum, compounded monthly. Okay, so here's our nominal interest rate. So we'll have to use the formula for compound monthly. So it's going to be your interest rate divided by 12. Okay, and then we'll adjust the time period into months. What will the investment be worth immediately after the last deposit? And then if Kyle makes no further payments but leaves the money in the account, how much money will be in the account on the 31st of March 2029? Okay, and these are very applicable real world problems because now you want to know if I'm making certain payments into my bank account regularly at the end of each month or at the start of each month, how much will I actually have after a certain time period? Okay, so let us draw a timeline to visualize how many installments Kyle makes from the 31st of January 2023 up until the last installment on the 31st of March 2028. Okay, so I start off with T0 and notice T1 here is going to be the end of the month for me. So essentially T0 would have been the 1st of Jan 2023 and the 31st of Jan 2023 would have been my T1. That's when I make my first deposit or when Kyle makes his first deposit. And notice from T1 to T12, that is a full 12 months. So you get to the 31st of December 2023. That'll be the 12th payment on that date that Kyle will make a payment of 500 Rand. And he's going to do this again for another 12 months and you'll get to December 2024. Another 12 months, another 12 months, all the way up until he gets to the 31st of December 2027. So essentially here, you've gone 4 years now. And you arrive at T60. So this is the 60th installment that is made on the 31st of December. And then if you do 3 more, T61, T62, you get January of 28. And then you get February of the year 2028. And then you get March 2028. So it'll be the 63rd payment that Kyle makes as his final one. So this is why timelines are so important to get correct. Okay, so from this timeline, we can see that he makes 63 equal payments of 500 Rand into the savings account. So now we can use the future value annuity formula to find out how much his investment will be worth after that. So here's the formula over here. I plug in my regular installments of 500 for X. 1 plus, now we need the nominal interest, which is 0.065 over 12 because it was 6.5% compounded monthly. Raised to the number of months, in this case 63 months according to our timeline, minus 1 all over the nominal interest rates. Okay, putting all that into your calculator, you will get 37,422 Rand and 47 cents. So that's how much Kyle's investment will be worth after 63 months of investing 500 Rand. Okay, and we want to actually know now, if he doesn't invest any more 500 Rand every month, he just lets that final amount sit until the 31st of March 2029. Well, 31st of March 2028, that's when he made his last investment. So that's going to be our T0. So that's going to be this amount here. So at T0, we currently have 37,442 Rand and 47 cents. So this is a new timeline, and it'll actually take 12 months to reach the 31st of March 2029. So what's happening is that the money is sitting in this account for 12 months without putting any more money into it. So now we simply use the normal compound formula, and that will be A equals P times 1 plus I to the power N. But remembering that it's still accruing interest at a monthly compound rate. So we put our nominal interest and 12 months to match up with that nominal interest. Putting that in, we see the grand total that Kyle would have after leaving that money for 1 year will be 39,928 Rand and 72 cents. So the key with future value annuities is to understand the formula really importantly, because X is telling you the number of installments you're making, I is telling you your interest rates, and N is telling you the number of periods based off your interest rates. Okay, and then we can substitute all that into the formula to figure out what our investment will be worth after so many time periods. Awesome. I'll see you in the next one.